in the last lecture, what we saw was that the basic operations on integers have the same complexity. That is, we saw that the time complexity of multiplying two n-bit numbers was bounded by the time complexity of of a squaring an n-bit number. So that should be S of n, which was in turn bounded by reciprocal computation of the reciprocal of an n-bit number, which in turn was again bounded by multiplying two n-bit numbers, which means if I have a good algorithm for any one of these operations, I have a good algorithm for each one of those. And observe that division is essentially computing the reciprocal, or maybe I could just put R there, reciprocal and followed by a multiplication. So that also has the same complexity. Now we would like to prove the same claim for the polynomials over one variable. So that is the ring Rx. Well, it could be any field really, as long as we assume that the all basic field operations take a constant time or order 1 time. So let us first of all observe that there is a very close relationship between the integer operations and the polynomial operations. Let us take a look at the way we represent integers. So an integer looks like ai b power I 0 onwards, where b is the basis we use to represent that integer. And of course, each of these ai's is in the range 0 to b minus 1. In case of polynomials of one variable, we write ai x power I 0 onwards. So they do look very similar, but actually dealing with polynomials is easier. For example, suppose you take two terms a1 or I would probably say a alpha xi plus a beta xi. If we add these two terms, in case of polynomials, all we have to do is on the other hand, if you have a term in the expansion of an integer, you have a alpha b power I plus a beta b power I, then this is a alpha plus a beta b power I. But this need not be a valid term. The reason is that this may be outside the range, namely 0 through b minus 1. So this could actually create terms of higher order. So it might go into terms corresponding to I plus 1, bi plus 1, bi plus 2 and so on. But that does not happen here. Now similarly, if you have multiplication operation, suppose you are multiplying these two, well, so all we have is, okay, let us just take more general situation, xi and b x power a beta x power j, then the right hand side is a alpha times A beta x to the power I plus j. Once again we have a similar situation, this is being multiplied to A beta bj. So, this becomes A alpha times A beta into b power I plus j. Once again the problem is that this number could exceed the range of 0 through b minus 1, and again it could actually go and affect the higher terms. So, the moral of the story is that dealing with polynomials is easier, and that is the reason that similarity will tell us that we can essentially use the same kind of algorithms, but they will be simpler in case of polynomials. Now, we will again follow the similar steps. We will try to show that the complexity of computing the reciprocal of a polynomial is same as multiplication of two polynomials. Well, let us first of all decide what do we mean by reciprocal of a polynomial. So, we want another polynomial. So, let us suppose we have a polynomial p ai xi, say I from 0 to n minus 1. Then and we will assume that the a n minus 1 is not 0. So, the degree is precisely n minus 1. Then we would like to find another polynomial q also of the same degree. So, we want something like this b I x power I going from 0 to n minus 1 such that p times q, remember q is supposed to be the reciprocal of p. So, this should be effectively 1, but in this case that would be x to the power, look, the degrees, the highest terms have power n minus 1 in the 2. So, it should be 2n minus 2 plus some error. Well, let us call it error in a sense that these are some things we cannot get rid of. What is this? Well, suppose we replace q by some other polynomial q plus f, then this will be pq plus p times f. The degree of f can be 0 or more, hence the degree of this term is greater than or equal to, the degree is greater than or equal to n minus 1. Because the degree of p is n minus 1, this has to be 0 or more. So, this is the case. What it shows is that we have access to the degrees n minus 1 or higher. So, we can actually make sure by choosing suitable polynomial we can get rid of all the terms up to n minus 1, but we cannot handle anything below n minus 1. So, the error can have degree less than or equal to n minus 2. So, this is the objective of computing the reciprocal of p, is to compute this polynomial such that we have this equation. Okay. So, now we will, as I said, we will adopt the polynomial, the algorithm that we had for integers, but actually it is a simpler algorithm. The objective is, given a polynomial p of degree n minus 1, we know that a n minus 1 is not 0. We split it into two subpolynomials and express p as p times x power n by 2. So, this contains all the terms of degree n by 2 or more, and this has degree less than n by 2, which is n by 2 minus 1 or less. And the objective is, of course, to compute a Q such that PQ is x to the power 2 n minus 2 plus some remaining term, the degree less than or equal to n minus 2. Well, in case n is 1, one more assumption we will make without much loss. Assume that n is a power of 2. In case it is not, you can always multiply by enough power of x, so that it raises its degree to a power of 2 minus 1, because the degree is n minus 1. If n is 1, then simply return 1 over a0. N is 1, which means p is just a0, and then q should be 1 over a0. So, the product will be 1. Otherwise, note that what we have done here is we have extracted the upper half of the polynomial. So, this has degree n by 2 minus 1. This we input this polynomial to the same subroutine and recursively compute its reciprocal q. And the next step is actually a copy of the similar step in the integer computations. This step, let me just make sure this is clear. What this says is that if q prime can be written as some a times x to the power n minus 2 plus b, which means all the terms for degree n minus 2 or more are put together as this by taking x power n minus 2 common, and this is the remainder which has degree n minus 3 or less. Then q prime divided by x power n minus 2 floor means a, which means that we ignore the lower terms because it is a floor in that sense, because all these b divided by this will have degree less than 0, and here we are getting a. So, with this interpretation of the operation, we compute q, and this is the desired polynomial which we will show. So, now we are going to show that this indeed does the job as desired. So, to prove that I need a small result which says that given f and g polynomials f times g divided by x power k floor minus f times g divided by x power k is of degree less than or equal to degree of f minus 1. The difference between these two has degree less than that of f. To prove this, let g be written as g1 x to the power k plus g2. All the terms of degree less than k are put here. So, this has degree k minus 1 or less. So, f times g divided by x power k is f times g1 plus times x power k plus f times g2 divided by xk. So, f times g by xk floor is nothing but f g1 plus f g2 xk floor. On the other hand, f times g over xk floor is g divided by xk floor is just g1, because this goes away and we get f times g1. So, the difference between these two is this term, and the degree of this term, is the degree of f plus, or actually this is less than or equal to, I will put a bound, degree of G2 is k minus 1 or less. So, at most k minus 1, and then we divide by x power k, it goes away minus k. So, this is at most degree of f minus 1 as we wanted. So, this is a result we will use. Okay. So, the proof of correctness goes as follows. Our goal is to show, that PQ, and which is same as P floor Q prime by x to the power n minus 2 is equal to x to the power 2n minus 2 plus R1 with degree less than or equal to n minus 2. Now, let us take a look at this term. This from our lemma is equal to P q prime over x n minus 2 plus a term R2 of degree less than or equal to degree of P minus 1. Degree of P minus 1, but the degree of P is n minus 1. So, this is nothing but n minus 2. So, what we notice is that these two things differ by a this is corresponding to this by a term of degree n minus 2. So, it is sufficient to prove that this term, so it is sufficient to show that P q prime by x to the power n minus 2 is x to the power 2n minus 2 plus some R3 with degree less than or equal to n minus 2. Okay, because these two already differ by only a term of at most n minus 2. So, now let us take this objective, and we know the value of q prime. So, P times q prime from the value of q prime, it becomes 2 2 QP x to the power 3n by 2 minus 2 minus q square p square. This looks like a expression for which we can do a whole square. So, we will add x to the power 3n minus 4 and subtract. So, we have added and subtracted this term. So, that becomes x power 3n minus 4 minus x to the power 3n by 2 minus 2 plus minus QP whole square. Okay. Now, recall that the small q is the reciprocal of small p, and from induction hypothesis it satisfies the condition that a reciprocal should satisfy. So, from induction p times q is x to the power n minus 2 plus r 4 with degree less than or equal to n by 2 minus 2. This is precisely what capital P and capital Q should satisfy. The only difference is now we are dealing with degree n by 2 minus 1 instead of n minus 1. Okay. So, let us use this in our expression. So, we get p q prime as x to the power 3n minus 4 minus x to the power 3n by 2 minus 2 and QP is q small p x to the power n by 2 and minus q p prime. Whole square, this square. Okay. So, let us plug in the value of QP from this expression. We are getting x 3n minus 4 minus x n by 2 minus 2 minus QP is x to the power n minus 2 plus this term. So, we have n by 2. So, that makes it x to the power 3n by 2 minus 2 plus R4 x power n by 2 minus q p prime square. These cancel and we are left with x power 3n minus 4 minus R4 x to the power n by 2 minus q p prime square. Let us find out the degree of these terms. R4 has degree n by 2 minus 2 at most, and this adds up to n minus 2 at most. N by 2 plus n by 2 minus 2, which is n minus 2. So, this has degree less than equal to n minus 2. Q has degree n by 2 minus 1. This has the same degree as small p, n by 2 minus 1. P prime also P prime has got degree n by 2 minus 2 or less. So, this has degree less than equal to n minus 3. So, overall the expression inside the parenthesis has degree n minus 2 or less, or the whole thing has degree 2n minus 2 or 4 minus 4. So, P q prime divided by x to the power n minus 2 is you subtract n minus 2, you are left with x to the power 2n minus 2 plus, or rather minus, this whole expression square divided by x to the power n minus 2. The term here has degree at most 2n minus 4, and you are dividing by x to the power n minus 2. So, this whole thing has degree less than or equal to n minus 2. So, what we get here is that p q prime over x to the power n minus 2 floor is indeed x to the power 2n minus 2 plus a term of degree at most n minus 2, and this is what we wanted to establish. So, this shows the correctness of our algorithm. Now, let us take a look at the time complexity. This process involves in the worst case the reciprocal of a degree n minus 1 polynomial takes say Rn time, then this takes multiplication, this involves one multiplication, this is of degree n minus 1, this is of degree n by 2 minus 1 into 2, which is n minus 2. So, in the worst case each term has degree at most n minus 1. So, this involves one multiplication of two polynomials each of degree n minus 1 at most. This is really not complicated, this just involves shifting of the term, because this just adds that much power, and this is receding the power, taking it back, and we have one recursive call of half size plus some linear operations, but we know that multiplication is at least linear. Well, it is not even linear, it is definitely worse than linear. So, we can absorb this term in this, and we can say this is less than equal to some C2 Mn plus R n by 2. We can absorb this here. If I expand this, I get this is less than equal to C2 Mn plus C2 M n by 2 plus C2 M n by 2 square and so on. Now, once again we know that this is worse than linear. So, m of n by a is greater than equal to m of n by a. So, use this and we can show that, okay, my mistake, the other way around, that this is worse because it is more than linear. So, this thing is equal to C2 mn plus C2 by 2 mn plus C2 by 2 square mn and so on. Hence, this can be, if this were an infinite series, which it is not, this can be expressed as C2 mn into the geometric series 1 plus 1/2 1 2 square and so on, which is less than C2 mn times 2, which is order mn. So, what we have proved is that the reciprocal computation does not take more than order of time that a multiplication takes. So, next we are going to show that the squaring does not take any more time than the reciprocal of a polynomial, and the algorithm that we are going to use is almost the same as the one that we had used for integers. We are computing the reciprocal of p into x to the power 2n minus 1. P has a degree n minus 1, so this has degree 3n minus 1. J is reciprocal of p plus 1 times x to the power 2n minus 1 and so on. So, now let us again show the correctness. Okay. From the previous proof, we know that I times p times x to the power 2n is x to the power 6n minus 2 plus r1 of degree less than equal to 3n minus 2. J times p plus 1 x to the power 2n is x to the power 6n minus 2 plus r2 also of degree at most 3n minus 2. So, we can now subtract one from the other and we get p times x to the power 2n times I minus j equal to j times x to the power 2n plus r1 minus r2. The degree of this is equal to n minus 1, this is 2n. This is the reciprocal of this term, so its degree is also 3n. This is degree is 3n minus 1. So, the right hand side has degree, so the total term has degree equal, and these have degree lower than 3n minus 2. So, nothing can cancel any part of this. So, this has degree 5n minus 1. These two together add up to 3n minus 1. So, we know that the degree of C, this is C, is precisely equal to 2n. Okay. So, let us just note down the degrees of these terms. This has degree 2n, this has to have degree 2n minus 1, reciprocal of C prime. So, this has degree 2n minus 1 and this has degree 2n minus 2. Okay. So, now the next step is, once again let us take these two equations and multiply them by p plus 1 and p respectively and subtract. So, p plus 1 times the first equation and p times the second equation. Well, if I multiply this by p plus 1 and I multiply this by p, the left hand side and subtract, then I get p times p plus 1 times x to the power 2n times I minus j, which is c. On this side, if I have p plus 1 and p, so I am left with x to the power 6n minus 2, that p plus 1. So, that 1 gives you this, and plus p plus 1 times r1 minus p times r2. So, we have this equation. The degrees of these terms, let us just put down that information. The degree of this is p as well as p plus 1 is n minus 1, and this of r1 and r2 is 3n minus 2. So, this becomes 4n, or rather less than equal to 4n minus 3, 3n minus 2 plus n minus 1. Okay. So, now what I need is to show that, okay, so we can just write down this as x to the power 6n minus 2 plus we have not used any other r. So, let us write down r3 of degree less than equal to 4n minus 3. Okay. Okay. Now, let us take the third step. Now, let us take a look at the third step. The third step is we are trying to find out what d prime is. So, let us compute d prime c. D prime c, which is d over x floor c, and that is dc over x floor from our lemma we wrote earlier, plus a term r4 of degree less than the degree of c, which is 2n. So, this is less than equal to 2n minus 1. Now, let us write down the degree of dc, sorry, the expression for dc prime. dc prime times c prime is c divided by x. That also can be written from our lemma as dc divided by x floor plus r phi, and the degree of this term is less than, here we had the degree of c, which is correct. Now, over here we have d outside, d has degree 2n minus 1. So, at most 2n minus 2. Okay. So, now if I subtract one from the other, I have d prime c minus dc prime equal to R6, this cancels out, and this has degree less than or equal to 2n minus 1. Okay. So, let us compute, okay, I will just rewrite this. Let us compute what is DC prime. DC prime, D happens to be the reciprocal of C prime. So, from the definition of reciprocal, and note that C prime had degree 2n minus 1, D had degree 2n minus 1. So, this is x to the power 4n minus 2 plus a term R7 plus of course R6. This term has degree less than or equal to 2n minus 2, because each of the D prime and C had degree 2n minus 1. Okay. So, together this has degree less than or equal to 2n minus 1, because there is R6 here. So, putting together I have expression for D prime C, which is x to the power 4n minus 2 plus R8 of maybe less than or equal to 2n minus 1. Now, I have got two interesting expressions, p into p plus 1 into x to the power 2n C. To compare this with this expression, I am going to multiply the both sides by x power 2n. So, I have got D prime C x to the power 2n is x power 6n minus 2 plus R8 x to the power 2n. Let us subtract this from this, we are going to get C times x to the power 2n D prime minus p times p plus 1, and this cancels out, and we are left with this has degree 4n minus 1, this has degree 4n minus 3. So, I have some R9 of degree less than or equal to 4n minus 1, the dominating degree is this. Let us take a, okay, I think I made a mistake, this is equal to, this is equal to this. Now, let us take a look at the left hand side. The degree of C was 2n, degree of x power 2n is 2n. So, this thing has degree equal to 4n, and this is a polynomial, cannot have a negative degree, but the right hand side has got degree 4n minus 1. So, this can happen only if this term is 0. So, D prime minus p times p plus 1 is 0, or D prime minus p is equal to p square. This is our A that we are returning. So, this proves the correctness of our algorithm. So, the time complexity of the squaring well, what we have done is we have computed two reciprocals. So, S of n, squaring a polynomial of degree n minus 1, we have computed two reciprocals of degree 3n each, because we multiplied p and p plus 1 both by x to the power 2n. So, the degree was 3n. We also computed a reciprocal of C prime. C prime had degree 2n minus 1. So, this is R of 2n. In addition to that, all we have done is some linear operations. So, this is of the order n. So, we can say that this is less than or equal to some constant times R of 3n. Okay. The fact that you can always do in a longhand division, you can always do in order n square. So, we know that this is no more than C times 3 square R of n. You can do in quadratic term. So, this is less than that. So, S of n is of the order R of n. Okay. So far we have managed to bind Rn by Mn and Sn by Rn. Now I am going to show that Mn itself can be bounded by Sn. So this is a very trivial task, just as in the integers. Let us take a look at two polynomials a and b and consider its square. Its square is a square plus b square plus 2 a times b. So a plus b is indeed 1/2 a plus b square minus 1/2 a square minus 1/2 b square. So you can, my mistake, a times b. So you can compute the product of two polynomials, say both of degree n minus 1, by squaring these three polynomials. Each is of degree n minus 1, because when you add the degree does not change. So you have done 3 squarings. So this simply shows that m of n is less than equal to some 3 times Sn plus some linear operations adding and so on and so forth. But again, you know, this is at least linear. So I can absorb this inside this and I have m of n as bounded by Sn. So now putting everything together, what we have found is that Mn is less than equal to some constant times Sn. Sn itself is bounded by reciprocation. So C2 times Rn, and Rn is bounded by Mn. Hence, all these 3 operations take the, you know, it is same Mn, so they have the same time complexity. And again, the division is nothing but one reciprocal and one multiplication. So this also has the same time complexity as all of these. So today what we have established is that again, whatever happens in case of integers, the same happens in case of polynomials, assuming of course that all the field operations, that is the operations on the coefficients, are assumed to be order 1. Later on we will show that we will give one efficient algorithm for multiplication, and that will imply that all these operations are also equally efficient. Without trying to prove anything more, we will get that. That is all.